This episode of The Reality Check is brought to you by HelloFresh. Forget takeout. HelloFresh delivers all the ingredients for delicious, healthy meals anyone can prepare at home in less than 30 minutes. And HelloFresh is giving our Canadian checkers 50% off their first order. Go to hellofresh.ca and use promo code REALITY50 to get 50% off your first order. That's hellofresh.ca, promo code REALITY50. This is your reality check.
Hi everyone, welcome to The Reality Check, the weekly Canadian show that explores a wide range of controversies and curiosities using science and critical thinking. This is the show for January 30th, 2017, and I'm your host, Darren McKee. With me, as usual, are Adam Gardner.
What's up, cuboids?
Christina Roach.
Hello.
And producer Pat.
Hi, everybody.
But not as usual, we have Stuart Robbins in a special crossover edition of Exposing PseudoAstronomy and The Reality Check. Welcome, Stu.
Hi, guys and gal. Thanks.
As usual, we have many interesting topics, so we're going to get right to it. Stuart, take it away.
For these segments, what I did was I've gotten a lot of feedback over the years from my own podcast. Those of you listening to this through my feed, the Exposing PseudoAstronomy podcast, you know what that is. Those on the TRC listening through that feed, if this stays in the show, it's Exposing PseudoAstronomy. And I've gotten a lot of feedback from people who want me to address various topics that I have in a massive list of requests. And many of them I still haven't been able to get to. And so when we talked about doing this crossover show, I asked if you guys would be willing to talk about some of those things that I haven't been able to get to yet, especially because a lot of them I thought were kind of shorter and could do really well with the reality check style treatment. So the first one is, we're told that black holes kind of can swallow anything, but some people think that we might be living inside of a black hole already, that it's our entire universe. So Darren, what's going on?
That's a great question, Stuart. So first, although your listeners probably know this, let's quickly clarify what a black hole is. It's a region of space from which nothing, including light, can escape. It reflects nothing, thus the blackness. General relativity indicates it's the result of the curving of spacetime caused by a very dense mass. Now, under quantum mechanics, black holes have a temperature and get smaller very slowly due to emitting Hawking radiation, so they actually can release some sort of energy, and then that causes them to shrink over time. Most black holes are made when a supergiant star dies, leaves behind a mass that is at least one solar mass, the mass of our sun. Stars die when they run out of hydrogen or other nuclear fuel to burn, and iron is produced. Iron does not give off energy, and therefore the star has no fuel, and in a short amount of time the star collapses. Forgive some of the Wikipedia quote here, but astronomers have identified numerous stellar black hole candidates and have also found evidence of supermassive black holes at the center of every galaxy. After observing the motion of nearby stars for 16 years, in 2008, astronomers found compelling evidence that a supermassive black hole of more than 4 million solar masses is located near the Sagittarius A region in the center of the Milky Way galaxy.
So just a quick note, it's Sagittarius A star.
Oh, I was going to say the asterisk, but good. Okay, I can say it again.
It's not meant to be a footnote. It's actually called Sagittarius A star.
The asterisk says pedantry is important.
Mm-hmm. Don't be a pedant.
And that's why one of us does this for a living. Now, One of the questions associated with what is a black hole is how fast a black hole can consume energy or matter. And it really depends on the size of the black hole and its proximity to anything else. And it's just going to be variable depending on those issues. Now, one website I saw that said a black hole is going to eat about one solar mass every 3,000 years. This one that I mentioned. So it's not really a lot, 1 sun every 3,000 years. Mm-hmm. Of course, the big question was, why would someone think our universe is in a black hole, or at least came from one? Mm-hmm. Well, typically, when people talk about the origin of the universe, they imagine an infinitely dense and hot point. That's sort of the common idea. Big Bang is expanding outwards, then you go backwards in time, and everything squishes down to some point. And I think this is because the math just goes to infinity, meaning there either actually was infinite energy at the beginning of the universe, or maybe the models are wrong. Anyway, when black holes are described, they are also said to take matter to an infinitely dense point, a singularity. Two singularities make a similar phenomena, maybe that's the logic, but that doesn't quite hold. Also, perhaps some people think of the event horizon of a black hole as something similar to the edge of our expanding universe. This is someone guessing about why people even think this in the first place. Mm-hmm. An article on National Geographic, which you can find linked on our website at trcpodcast.com,
great website,
discusses the ideas of physicist Nikodem Poplaski at the University of New Haven. He thinks the black hole singularity may just be due to math, but the origin of our universe is different. The compacting process in a black hole halts, according to this physicist, because black holes spin. They spin extremely rapidly, possibly close to the speed of light, and this spin endows the compacted seed, as he's calling it, with a huge amount of torsion. It's not just small and heavy, it's also twisted and compressed, like one of those jokey spring-loaded snakes in a can. But like a universe.
Peanut brittle.
Exactly. Peanut brittle. Our universe is kind of brittle. Which can suddenly unspring with a bang. Make that a big bang. Or, what this physicist says, a big bounce. Like that peanut brittle. It's possible, in other words, that a black hole is a conduit. A one-way door, says Dr. Poplawski, between two universes. This means that if you tumble into the black hole at the center of the Milky Way, it's conceivable that you, or at least the shredded particles that were once you, will end up in another universe. This other universe isn't inside ours, as Dr. Poplawski. The hole is merely the link, like a shared root that connects two aspen trees. Well, that sounds good. And you know, some of that terminology, it is conceivable. Like, oh, really? You can conceive of it? Well, so Star Wars is conceivable, as Adam knows, but it's still not real. Now, Brian Koberlin, who is a bit less keen on this idea, says a couple things. First, quote, "To begin with, the universe did not begin with an explosion from a single point. It was definitely very hot and dense in its early period, but it didn't begin as a singularity. In fact, there is debate whether black holes themselves have singularities. So while there are similarities between these two ideas, we can't simply equate them. This is a reminder that everything is debatable in all things."
Well, it seems to me that it's like he's using language to say, because we use the same terms for these two things, that must mean they're the same, when that might not really apply.
Of course. And as we know, it's pretty hard to get a lot of good evidence for a lot of the nice math that works out in astronomical theories.
Oh, yeah.
If we think about being in a black hole, it just doesn't quite fit. And this is a quote from Brian. "Our universe isn't collapsing in on itself, it's expanding at an ever-increasing rate, so it doesn't have the necessary structure to be the interior of a black hole. But there are some models that do propose that our universe was formed by the black hole of another universe. These models are very speculative, but generally propose that the super-dense interior of a black hole could create a baby universe that expands to become its own universe. Technically, you could say this new universe is in quotes, the black hole that spawned it, but because of the bendable nature of space and time, that's not particularly meaningful. The new universe would in no way be limited by the size of the black hole and would exist on its own once it formed." So in conclusion, this is a very interesting idea, and both these commentators kind of agree. One physicist thinks it's a good idea, another one's like, well, it's an interesting idea, but there is actually no evidence to support it. Cosmological theories are delightful candy for the mind, but they really aren't filling because there often isn't anything of substance to back them up.
Nice analogy.
Thanks, Darren, for poking holes in that perhaps filling or maybe not so filling idea. If we're not in an endless wasteland of quantum fields and virtual particles and maybe singularities with a little bit of twist thrown in, maybe we'll be visited by other beings. Pat, can you tell us something about the Drake equation?
Well, so before we get to the Drake equation, we have to do a bit of background. Frank Drake is an American astronomer who is interested in something that had been proposed by physicists Giuseppe Cacconi and Philip Morrison. In a 1959 paper in the Journal of Nature, they proposed that radio telescopes had become sensitive enough to pick up possible radio transmissions from other civilizations. They also suggested that these signals might be transmitted at wavelengths of 21 centimeters, something known as the hydrogen line. And if you want to know what that is, you should probably ask Stuart.
Yeah, well, so we also like to sometimes call it the cosmic watering hole. It's basically, It has to do with quantum mechanics. It's where there is a particular line in the emission spectrum of hydrogen, and people think that that might be sort of the watering hole, where a lot of civilizations might transmit if they're looking for other civilizations, because it's sort of one of those universal things like prime numbers, as opposed to randomly transmitting at, 109.4 FM.
Right. So in 1960, Drake was the first guy to start looking for those signals at the National Radio Astronomy Observatory in Greenbank, West Virginia. Then in 1961, the National Academy of Sciences organized a meeting on the search for extraterrestrial intelligence. The meeting included people like Carl Sagan and previously mentioned Philip Morrison. Frank Drake was the host of the meeting. Here's a quote. as I planned the meeting, I realized a few days ahead of time we needed an agenda. And so I wrote down all the things that you needed to know to predict how hard it's going to be to detect extraterrestrial life. And looking at them, it became pretty evident that if you multiplied all these together, you got a number, N, which is the number of detectable civilizations in our galaxy. This was aimed at the radio search and not to search for primordial or primitive life forms. So essentially, the Drake equation is a way of organizing all the questions that Drake thought were important to consider in order to arrive at an estimate of the number of active, communicating civilizations in our galaxy, and the goal was to stimulate conversation among the scientists. So looking at the equation itself, it looks like a bit of gibberish. We'll break it down. It has 8 pieces. N equals. This is what we're trying to solve for. The number of detectable, intelligent, communicating civilizations in the galaxy. R is the rate of yearly star formation. A simple estimate just takes the total number of stars in our galaxy and divides by the age of the galaxy. And then this is multiplied by FP, which is the fraction of those stars with planets. It's hard to have life without planets.
Maybe.
So then we multiply by NE, and this is the number of those planets per solar system suitable for life. So for example, one main criteria would very likely be liquid water. And then this is multiplied by FL, the fraction of those planets on which life actually appears. And then that's multiplied by FI. That's the fraction of those planets on which intelligence arises. And then we multiply that by FC. And that's the fraction of those that would have the desire and the technology to communicate. And then finally, this is multiplied by L. And that's the length of time that these civilizations would be communicating. I've seen a couple of different claims for what the scientists used in 1961 to fill out this equation. The Wikipedia entry for the Drake equation suggests that they came up with a minimum of 20 and a maximum of 50 million.
Yeah.
In a 2010 BBC documentary called The Search for Life, The Drake Equation, Frank Drake himself is asked to plug in the numbers that they used in 1961. He said that they estimated the rate of star formation was 10 per year. He suggested that they had indirect evidence about the fraction of stars which had planets from binary stars, so they used 0.5. He said they used 2 for the number of planets which could sustain life. And that was based on our solar system and the notion that Mars might have been able to retain an atmosphere if it had been a bit more massive. So you've got the Earth and Mars.
Not bad.
He then goes on to say that chemical experiments suggest that given a planet like Earth and enough time, life would appear one way or another. So they use the fraction of 1.
Wow.
The fraction of those that would give rise to intelligence, they guesstimated at 0.5. The fraction of those that would develop detectable technologies was based on our own history, and again, they used the fraction of 1. Finally, he suggests that 10,000 years for the length of the time that would be detectable was, quote, a favorite guess. So after plugging all that in, the number he offers in the documentary is 50,000 civilizations in our galaxy.
Wow.
So if you weren't already familiar with the Drake equation, I expect you now know why it's met with some skepticism. Star formation rates are pretty well understood, and we have some understanding about exoplanets and even which ones might support life, but assigning values to everything else in the equation is pretty much pure speculation. It's hard to make estimates when we know of only one planet with life, never mind intelligent life. We can't draw any conclusions from the Drake equation, and some critics suggest that since the margin of error is so large, it really isn't useful. It's also tied to detecting radio signals, and that's something Adam covered on a previous episode of TRC in the past when we looked at SETI on episode 308. Now, it's worth mentioning that there have been several suggestions for revisions or additions to the original equation. For example, astronomer Sarah Seeger proposed an equation that focuses on biosignature gases, or gases which are produced by living organisms. So that's the Drake equation. Criticism aside, the reason Drake came up with it was to stimulate conversation about the likelihood of intelligent life elsewhere in a structured way. It's not to give a definitive answer.
Yeah, and I I would actually add to that the first three terms have been dramatically revised since they first proposed this. I mean, the rate of star formation in the galaxy, cosmologists have been studying that for over a century, but this idea of the number of planets in a solar system has also just been blown out of the water, completely revolutionized with the discovery of all of these exoplanets just in the last decade or so. And then the fraction of planets or bodies in the solar system that can support life has also completely changed, because when Drake was initially coming up with this, or when the people in the room were, they didn't even think about habitable moons. So I mean, we can think of Europa, we could think of Enceladus. I mean, these are moons of Jupiter and Saturn that could potentially harbor life, and they weren't even thinking of that at the time. I mean, that was before the movie Avatar, so...
But when you talk about Europa, Stuart, not that I'm going to call an astronomer out on anything, Europa might be able to harbor life, but intelligent life?
We don't know. I mean...
Right.
I very much agree with the criticism of the Drake equation in the sense of the other terms we have absolutely no idea. We have an N of 1. In other words, we have us to go off of. And for us, we can't really think of intelligent technological life that, for example, could live in water, because water conducts electricity very, very well. So it's hard to think of how a technologically advanced civilization could develop if it were water dwelling, which is what we would imagine for anything under the surface of the ice in Europa or Enceladus. So it's really hard to speculate about this stuff.
I also think it's interesting that we've given ourselves the standard, as we humans typically do, when it could be 50, 100 years, we're more cybernetic, enhanced through robotic technology and artificial intelligence, blending with humans, and then we look back like, that really wasn't intelligent back then, so that didn't count.
Where's my jetpack, damn it? Mm-hmm. Yeah, well, that also gets into things like the Fermi paradox, which might be a future episode. Or actually, have you guys talked about it on TRC? Do you know?
We haven't, but I read an article today that suggests that the Fermi paradox was neither something proposed by Fermi nor a paradox.
Yeah, that's true. But
it was on my to-do list, or one of us anyway.
Thanks, Pat, for a fascinating piece of philosophical and observational musings put into the form of an equation. If aliens were to ever come and visit us, might we want some sort of shielding in case they were evil and out to kill us? So I'm going to talk about a recent article that came out in Physical Review Letters about Earth's protective barriers that has absolutely nothing to do with Doctor Strange, for those of you who recently saw that movie and are thinking about magical protective barriers. In this case, it's not magic, it's science. In November of 2016, a news article was published entitled "Solar Flare Radiation Burst Cracked Earth's Magnetic Field, Caused Radio Blackouts." It was talking about an article that was published in the journal Physical Review Letters, and I skimmed the PhysRev article because it is frankly full of a huge amount of jargon and written by non-native English speakers. 2 recipes for a very dry, boring, and hard-to-read article. Here are the basics. Earth is surrounded by a magnetic field. The magnetic field is dipole in shape, similar to your normal bar magnet that most of you are probably familiar with and may have played with as kids, and had metal iron filings and saw all the cool little magnetic field lines. That's basically what Earth's magnetic field kind of looks like, except there are little modifications to that. Earth's magnetic field can deflect particles, which are magnetically charged around the planet. So basically, think of it as you have a big cushion in front of the planet, and if a magnetically charged particle comes streaming towards our planet, that big cushion can deflect that particle around us. But it can also funnel those particles into the poles, because that's where the magnetic field lines dive back into the planet. When these charged particles interact with our atmosphere, that's when we can see the aurora. It's pretty, and it's also pretty cool. The magnetic field fluctuates, though. Think of a balloon. It's usually a nice, normal balloon-like shape, but if you spray that balloon with a water hose, it's going to deform. And if you spray it with a lot of water hoses in different directions, it's going to get all wiggly woggly and deform a lot. And that same thing happens with Earth's magnetic field. But unlike a balloon, that deformation of Earth's magnetic field can decrease our field strength in certain places for quite a while, a couple hours, and it can also deflect Earth's magnetic field a large amount. The field is commonly thought to extend very roughly 7 times the planet's size out into space before you basically wouldn't be able to measure it at all, and you would be measuring the interplanetary magnetic field from the sun. But a very powerful release of charged particles from the sun, basically if the sun burps, it can deform our magnetic field. And so that magnetic field of our planet can deform so much that it dips into the atmosphere when it normally shouldn't. And that is a huge deflection of the magnetic field. It doesn't actually break or crack, it just deforms. So what the article that will be linked to in the show notes, both on my website, podcast.sjrdesign.net, and trcpodcast.com,
Great websites.
what it talks about is that there was a telescope that tracks particles from outside of our solar system that happened to make it to Earth's surface. So what do I mean by that? Because I realize now as I wrote that makes no sense. So what I mean by this is that we have particles from Earth, we have particles from the sun, and we have particles from beyond the sun. We call those galactic particles, like galactic cosmic rays, and has all these fancy stuff. Fancy names. It just means that these are particles that are coming from beyond the solar system. And the way that we know that they're from beyond the solar system is usually their energy level. So if they're really energetic, they can make it through the sun's own magnetic field and they can impact Earth. So what these telescopes do on Earth is that they monitor particles with these really, really big energy levels in order to measure, basically, how strong or weak the sun's own magnetic field is, as well as Earth's magnetic field. So on June 22nd of 2015, there was a massive outburst from the sun that struck our planet's magnetic field. What the researchers found was that during that impact of these charged particles from the sun on Earth's magnetic field is that their detection of particles with these really high energy levels that are from outside of the solar system was significantly larger than they normally see, and significantly larger than they thought that they should see. So they used the data, they ran some models, and what they concluded was that the magnetic field of Earth had been compressed by a factor of 17. So that means that it was crushed effectively by a large amount and deflected into Earth's atmosphere as opposed to extending about 7 times the planet's size beyond the surface of the planet. That was the only way they could get so many particles that should have been blocked by Earth's magnetic field to actually strike their detector in their telescope. So now that I've explained it, it seems probably ridiculously technical and probably rather mundane, but what's important is that it adds to our body of knowledge about what can happen to our planet's magnetic field when our sun decides to burp.
Now, Stuart, I've heard it suggested that sort of one thing to keep in mind when you're looking for intelligent planets, Drake equation type of stuff, that you would need to consider a planet that has a similar magnetic field than us. So are these particles that are coming from elsewhere in the galaxy potentially a threat to us or to our life or anything on Earth? Yes.
With that, it was a very long yes, and that's because it's a very qualified answer. I can't say no because it's not that they aren't dangerous. For example, if a nearby supernova goes off, the charged particles from that supernova are pretty much going to look at Earth and look at our magnetic field and say, yeah, right. And the magnetic field will pretty much just get crushed. The particles will impact that half of the planet facing the supernova, and it could basically wipe out all life on that side of the planet in an instant. This is actually covered in Phil Plate's Death from the Skies book. It becomes an issue also if you want to go beyond the planet and beyond the magnetic field. So, for example, the astronauts on the International Space Station, they are well within Earth's magnetic field. most of the time, so they're fine. But if we want to go to Mars, we have an issue. And I actually addressed this recently on my podcast on an episode about radiation. I want to say it was episode 154. And so, I mean, this is a case where if you don't have shielding inside of your spacecraft or on the outside of your spacecraft and the sun burps, you're in for a load of trouble. Getting back to the initial question, though, about finding a planet that is suitable for life, should it have a magnetic field? Probably yes, unless you want to go a few tens or hundreds of meters below the surface in order to create your habitat.
Thanks for having us, Stuart, and thanks again for joining us, listeners, on this interesting hybrid show of Exposing PseudoAstronomy and the Reality Check. We hope you enjoyed the diversity of segments, and we'll try to talk about space more in the future, because it's fun to talk about. Until next time, think better to act better.
Peace out, cuboids.
Stay classy and not smartassy.
Space is vast. Don't be a smartass.
Nicely done. Good night, everyone.
For show notes or to discuss this episode, visit our Facebook page and website at trcpodcast.com. For general inquiries or to send a topic or parody suggestion, email info@trcpodcast.com. Help support the show by leaving a review on iTunes and liking us on Facebook. Follow us on Twitter at TRC_podcast.
Outtakes.
All right, so it's here where you insert music or whatever. Okay.
Pat's job has never seemed so glamorous.
The bumper music is kind of...
I'm sure that's probably going to be an outtake on your show. All right, so
Here's where you do some work or something, whatever, Pat.
yeah.
Welcome to an atypically funny episode of the PseudoAstronomy podcast.
Yeah, well, normally it's me doing a monologue. All right.
Well, you invited a bunch of people on to talk about astronomy that aren't astronomers. What did you expect, man?